In this lecture, I'll talk about the joy of counting. And this mathematics can really bring you joy because we're going to see how you can use this to figure out problems that might be of interest to you, such as the number of possible outcomes in a horse race, the chance of winning the lottery, even figuring out your odds in poker. We'll be able to determine using the techniques of this lecture. Now, when I think of counting, I think of basically two principles. There's the rule of sum and the rule of product. The rule of sum says this: if I own 5 long sleeve shirts and I own 3 short sleeve shirts, then the number of shirts that I can wear on any given day would be 5 plus 3, the sum of those numbers. Whereas if I'm thinking of, let's say I own 8 shirts, and let's say I own 5 different pair of pants, okay, and I don't think about color coordination, which is true of most mathematicians, I'm afraid, then the number of possible outfits that I can wear, I'd have 8 shirts and 5 pair of pants, would be 8 times 5. I'd have 40 outfits. And if I had 10 different ties that I could wear, well, then that would multiply the number of possibilities, the number of possible triples, shirts, pants, and ties, by a factor of 10. I have 8 times 5 times 10, 400 different outfits. Okay, we'll start with simple questions, like how many ways can I arrange a bunch of letters? Okay, like the letters A and B can be arranged 2 ways, right? A, B, and B, A. How about A, B, and C? Well, those could be arranged 6 ways, because we have ABC, BAC, CAB, ACB, BCA, CBA, as presented here, right? So there are 6 ways of doing that. There are 24 ways of arranging A, B, C, and D, as we've displayed here. Now, what do these numbers have in common? You might recognize these numbers from the previous lecture, right? We have 1 is 1 factorial, 2 ways was 2 factorial, 6 ways is 3 factorial, 24 ways is 4 factorial. So why should that be? Well, think of if there are 6 ways to arrange A, B, and C. Let's figure out the number of ways of arranging A, B, C, and D. For every one of those 6 ways, there are 4 ways of inserting the letter D. Right? So starting with A, B, C, we could put D in the first position, the second position, the third position, or the fourth position. That's going to lead to 4 new ways of arranging A, B, C, and D, where A, B, and C are still in their original position. Whereas if I took, say, the next set of numbers, A, C, B, there are still going to be 4 places that I can insert the letter D among the letters A, C, and B. So for every one of those 6 actions that we can start with, for any one of those 6 arrangements, we can follow that up with 4 new decisions. Where does the D go? So that's going to be 6 times 4, 24, or 4 factorial ways of doing that. As we've noted before, factorials grow awfully large. Here are the first 12 factorials. There are, for instance, 12 factorial over 479 million ways of arranging the first 12 letters. If you had 12 books on a bookshelf and you said, how many different ways can I arrange those 12 books on a bookshelf? There are, believe it or not, over 479 million different ways you can do this. Another way of thinking about this, maybe more graphically, is imagine I have 5 cards. Okay, this is a more direct way of thinking about arranging. I'm going to take these 5 cards and I say, how many different ways can I arrange them on the table? Okay, so your first choice is, well, which card are you going to put down first? Okay, I've got 5 choices for what card I'll put down first. Once I've chosen that, how many choices do I have for the next card? There are 4 choices. So there are 4 choices for what card goes next. Once you've made those 2 decisions, you've got 3 choices for what goes next, then 2 choices for what goes next, and finally 1 choice for the last card. Therefore, the total number of possibilities is 5 times 4 times 3 times 2 times 1, 5 factorial. And in general, the number of ways of arranging n different objects is going to be n factorial. Okay, let's do another problem. Let's say, how many different zip codes are possible. Okay, so a zip code consists of 5 digits. The first digit is anything from 0 to 9. The second digit is from 0 to 9, etc. The last digit is from 0 to 9. How many different ways can you create a zip code? Well, the first digit, we have 10 choices, anything from 0 to 9. The second digit has 10 choices. The third digit has 10 choices. The fourth digit, the fifth digit, those each have 10 choices. Therefore, the number of possible zip codes is 10 times 10 times 10 times 10 times 10, 10 to the fifth, 100,000 possible zip codes. Suppose I change the question now. Suppose I say, all right, how many zip codes where none of the numbers are allowed to repeat? So for instance, the first digit, we have 10 choices, that's true. The second digit, now we only have 9 choices because it has to be different from the first digit. So for instance, if the first digit was 4, then the second digit could be anything other than 4. Let's say we made that the number 2, okay? Once we've chosen the first 2 digits, then how many choices do we have for the third number? Well, there are going to be 8 possibilities. In my mind, I like to actually pick a definite number, so let's say it's 3 as the third digit of the zip code. Okay, now the next digit, I have how many choices? 7 choices. And for the last digit, I'll have 6 choices. So the number of 5-digit zip codes where none of the numbers are allowed to repeat would be 10 times 9 times 8 times 7 times 6 would be 30,240 possible zip codes. Okay. Let's apply this to horse racing, okay? A simple problem, really. In a horse race with 8 horses, how many possible different outcomes are there? Where an outcome is a horse finishing first, another horse finishing second, and another horse finishing third. Win, place, and show. Okay, well, there are 8 choices for the horse that comes first. Once you've done that, there are 7 choices for the horse that comes second. And once you've done that, there are 6 choices for the horse that comes third. And so there are 8 times 7 times 6, 336 possibilities for the horse race outcome. Here's another question. How many possible license plates are there if a license plate comes in 2 varieties? Let's say type 1 license plate have 3 letters followed by 3 numbers, and a type 2 license plate has 2 letters followed by 4 numbers, like the examples we see. So first of all, let's answer these questions into 2 cases, because your license plate is either of type 1 or of type 2. So the rule of sum is going to apply here. How many type 1 license plates are there? Well, let's see. For the first 3 letters, we have 26 choices for the first letter, 26 for the second, 26 for the third. And then the 3 numbers that follow it, there are 10 choices, 10 choices, 10 choices. Multiply those numbers together and you get 17,576,000 different license plates. Incidentally, I'm assuming that we can distinguish between the letter O and the number 0, the number 1 and the letter I. We won't pretend that there are any complications with that. Okay, next, how many license plates are there of type 2? Well, this time we have 2 letters followed by 4 numbers. So we have 26 choices for the first, 26 for the second, and then those remaining 4 numbers are 10 choices, 10 choices, 10 choices, 10 choices. So altogether, 26 times 26 times 10 to the 4th, 6,760,000 possibilities. Therefore, the total number of license plates when we combine type 1 and type 2 is 24,336,000. But what I like about combinatorics, that's the mathematics of counting things, combinatorics, is that you can often take a problem and solve it lots and lots of different ways, and if you're careful, you'll always get the same answer. So for example, in this last problem we did, we can actually do it in 1 step instead of taking 2 steps. For instance, the first letter is 26 choices. The second letter is 26 choices. Whether we're of type 1 or type 2, we've got 26 times 26 ways to get started. But what about the third item on the license plate? Well, it could either be a letter or a number. So how many choices do I have for that third item on the license plate? 26 plus 10, 36 possibilities. And then the remaining 3 items, those all have to be numbers. So I have 10 choices, 10 choices, 10 choices. When you multiply those numbers together, 26 times 26 times 36 times 10, 10, 10, we get the exact same answer we had before, 24,336,000. Same problem as before, but now all the letters have to be different. Now we have 26 choices for the first letter, 25 choices for the second letter, but that third item could be any one of 24 letters or 10 numbers. Therefore, there are 34 possibilities for that third item. And then the last 3 items all have to be numbers, and so we have 10 choices, 10 choices, 10 choices. Multiply those numbers together, and we get 22,100,000. If all the letters and numbers must be different, then we can still do it in one step, but we have to pursue a more creative strategy. We have 26 choices for the first letter, 25 choices for the second letter. Okay, I don't yet know what the third item's going to be, so let's skip that third item and go on to the fourth item. The fourth item, there are 10 choices for it, because it has to be a number, 9 choices for the next number, 8 choices for the last number, and now we go to item number 3. Item number 3 can be a number or a letter. So there are 24 choices for the letter, 7 choices for the number, and therefore 31 possibilities for item 3. So we can multiply all those together to get 26 times 25 times 31, 1098, to get our answer of 14,508,000. Okay, let me live up to my promise and talk about winning the lottery. In California, they have a game called Super Lotto Plus, and it goes like this. Step 1, choose 5 numbers from 1 through 47. Step 2, choose a mega number from 1 through 27. That mega number is allowed to be one of the 5 numbers that you've picked, or it could be a different one. It's up to you. Step 3, cross your fingers. All right, for example, let's say I pick the numbers 2, 3, 5, 8, and 13. Those, by the way, are Fibonacci numbers, and I'll have more to say about those later. And the mega number 21. You'd say, well, how many ways can the state pick its numbers? And then we'll see which of those are mine. So the state has 47 choices for its first number, 46 choices for its second, 45 for its third, 44 for its fourth, and 43 for its fifth. So there are 47 times 46, 45, 44, 43 ways of picking the first 5 numbers. And then the state has 27 ways to pick the mega number. So that sounds like that would be the right answer, but unfortunately, you have overcounted. That answer is wrong. Because if I said the state, let's say the state chose the numbers 1, 10, 20, 30, and 45. That turns out to be the same as the state picking the numbers 10, 20, 45, 30, and 1, right? They're the same group of 5 numbers, but you've counted them as different. So how many ways could you have arranged those 5 numbers and still had the same set of 5 numbers? Well, by the way of dealing through the cards, we saw there were 5 factorial ways of arranging those numbers. So the correct answer to this problem takes the original number that we came up with and divides it by 5 factorial. Okay? This sort of reminds me of the problem of farmer brags to another farmer and says, I could look in your farm and instantly count the number of sheep that you have. Second farmer is skeptical, says, okay, how'd you do it? Hey, show me that you can do it. So farmer walks in and says, I see you've got, exactly 87 sheep. He said, why, that's amazing. How did you do that so quickly? He said, I counted the number of legs and divided by 4. So maybe that's not funny, but that's the analogy to the problem that we just did. That is, we first counted the numerator, overcounted the problem, and then divided by the denominator to get things right. Okay? So we saw there were 41,416,353 ways of the state picking its numbers, only one of which are your 5 numbers, right? And therefore, your chance of winning is just 1 over 41 million, which is pretty small. Incidentally, when we deal with products like 47 times 46 times 45 times 44 times 43, Another way of expressing that, a little bit mathematically cleaner, is to take the numerator and the denominator and multiply them by 42 factorial. So the numerator now looks like 47 factorial, and the denominator looks like 42 factorial. So those quantities are the same thing. They just looks a little bit nicer in the second form. And the number of ways of picking 5 different numbers out of 47 is that quantity we have divided by 5 factorial. So you get this rather pretty looking expression, 47 factorial divided by 5 factorial, 42 factorial. That's the number of ways of picking the first 5 lotto numbers. In general, the number of ways to pick k objects from n objects by the same logic that we went through, where the order is not important, is n factorial divided by k factorial times n minus k factorial. That's denoted n choose k. Mathematicians call that n choose k because it's a number of ways from n objects that you can choose k objects. So for example, in the game of poker, how many 5-card poker hands are there? Well, you have 52 cards. You're going to choose 5 of them. The order that you get the cards is not important. We're playing a game like 5-card draw, not a game like 5-card stud, where order would be important. And so the number of ways of picking 5 out of 52 is 52 choose 5, which has formula 52 factorial divided by 5 factorial, 47 factorial, which is 2,598,960, which is a pretty awesome number. So you might ask, well, what are your chances of being dealt a specific kind of hand in poker? For instance, what are your chances of being dealt a flush, which is 5 cards of the same suit in poker? Well, to answer that question, we say, what choices do we have to make? First of all, how many choices do we have for a suit? If the poker hand is going to be 5 cards of the same suit, how many choices do I have for the suit? 4 choices, right? It could be a spade, heart, diamond, or club. Once you've chosen that suit, how many ways can you choose the rest of your cards? Well, let's suppose you chose the suit of hearts, okay? Now, how many ways can you pick 5 hearts out of the 13 hearts in the deck? Well, by definition, that is 13 choose 5. 13 factorial over 5 factorial, 8 factorial. So you multiply those numbers together and you get 5,148. And therefore, your chances of being dealt a flush in poker would be 5,148 divided by the 2,598,960 possible different poker hands. That's about 0.2%. About 1 out of every 500 poker hands will you be dealt a flush. All right, well, let's try a different poker hand. How about, what are the chances of being dealt a full house in poker? All right, so what's a full house? A full house consists of 5 cards, 3 of one value and 2 of another value. Okay, so how many ways are there to deal a full house? Well, the first decision that you have to make is to choose which value is going to be triplicated. And there are 13 choices for the tripled value. Okay, let's say you went with queens. Okay. Once you've chosen queens as the tripled value, then you say, how many ways can you pick the duplicated value, the value that appears twice? Well, there are 12 ways of doing that. Let's say you went with 7s. Okay. Now, once you've chosen queens and 7s, we have to decide the suits of those cards. We'll start with the queens. How many ways can you choose 3 suits for those 3 queens? Well, the answer is 4 choose 3. That is, from the 4 queens that you have, spade, heart, diamond, and club, choose 3 of them. Now, 4 choose 3 is equal to 4. You could count them out. You know, spade, heart, diamond, spade, heart, club, and so on. Similarly, how many ways can we choose 2 7s out of the 4 7s that we've had? Well, we have to choose those suits. 4 choose 2 ways of doing that. That's numerically equal to 6. So the number of full houses is 13 times 12 times 4 times 6. Multiply them together, you get 3,744, which is a smaller number than what we had for finding flushes, right? With flushes, we had 5,148 flushes. With full houses, we have 3,744. Only about a 1 in 700 chance of being dealt a full house. And that's why in the game of poker, the full houses are more valuable than flushes because they are more rare. You're less likely to have those dealt to you. Okay, one more question. This is an easy one to get wrong. How many 5-card poker hands have at least one ace? Okay? How many have at least one ace? I'm going to give you the tempting answer, which unfortunately is wrong, but it's one that people make, a mistake that my students make so often that I have to show it to them first, so they're less likely to make it on their test. Okay, so here's the tempting way to answer that question. You say, how many poker hands have at least one ace? Well, first I have to choose an ace, then I have to pick 4 other cards from the remaining 51. Okay, how many choices do I have for that first ace? 4 choices. Let's say I pick the ace of spades. Then, from the remaining 51 cards, I have to pick 4 of them. So there are 51 choose 4 ways of doing that. So it seems very sensible that the answer would be 4 times 51 choose 4. Unfortunately, the logic in that is incorrect because let's suppose that, here's a hand that has at least one ace, right? There's the ace of spades, and let's pick 4 other cards. All right, I'm going to be a little deliberate on the 4 other cards here. Let's say the 4 other cards were the 4 of diamonds, the 6 of diamonds, the 4 of clubs, and the ace of diamonds. Okay? So that's a hand that has at least one ace. But that's the same hand as if you had first chosen the ace of diamonds and then chosen these 4 cards, the ace of spades, 4 of clubs, 6 of diamonds, 4 of diamonds, as your remaining 4 cards. You see? So you were counting, there is no first ace in this hand. This is a 5-card hand. Order simply doesn't matter when it comes to a 5-card poker hand. So to say, first choose an ace, your first card, and then pick 4 other cards is bringing order into a problem where order does not belong. Okay, so that's why the first answer I gave you was wrong. What's the correct way of doing it? The correct way of doing it is to break the problem down into 4 cases. I want to count the number of aces that are in the hand. Right? We have to have at least one ace. So I'm going to first count those poker hands with 1 ace, then count those hands with 2 aces, then 3, then 4, then apply the rule of sum to add all those hands together. So for example, how many poker hands have exactly 1 ace? Well, first we choose the ace that we're going to use. Exactly 1 ace. So there are 4 aces in the deck. We've chosen one of them to be our ace. Next, we have to pick 4 non-aces in the deck. How many non-aces are there in the deck? There are 48 of them, right? You have to choose 4 of them. So the number of ways of picking 4 non-aces is 48, choose 4. Therefore, the number of poker hands with exactly 1 ace is 4 choose 1 times 48 choose 4. How many poker hands have exactly 2 aces? Well, this time you first choose your 2 aces, 4 choose 2 ways. Once you've done that, you have to choose how many more cards? 3 more cards from the remaining 48. How many ways can we do that? 48 choose 3. Therefore, the number of poker hands with exactly 2 aces is 4 choose 2 times 48 choose 3. Similarly, the number of poker hands that have exactly 3 aces is 4 choose 3 times 48 choose 2. First you choose the 3 aces, then you choose the 2 non-aces. Finally, the number of poker hands with exactly 4 aces is 4 choose 4, which is 1, times 48 choose 1, which is 48, right? The number of ways of picking one thing out of 48 is 48, and therefore the number of hands with exactly 4 aces is 48. It's good sometimes, by the way, when you see a number like 48, to give it a sensibility test, like, does that make sense? How many poker hands have exactly 4 aces in it? Well, since the order of those 4 aces doesn't matter, all that matters is what is the odd card, the non-ace, and there are 48 non-aces in the deck, so that answer makes sense. So adding all those cases together, we get 886,656 different poker hands. Now, like I said at the beginning of this lecture, one of the great things about combinatorial problems, counting problems, is that you can do these problems many different ways. So here's I think, an even slicker way of doing that last problem. How many hands, the question is how many hands have at least 1 ace? But let's instead answer the question, how many hands have no aces? And then we'll subtract that from the total amount. Okay? How many hands have 0 aces? Well, that's easy. There were 4 aces in the deck, so there are 48 non-aces in the deck. Choose any 5 of them. If you choose, how many ways can I choose 5 things out of 48? By definition, 48 choose 5, which is 1,712,304. Once you have that, we can then say, if those are the number of hands that have 0 aces, then when I subtract that from the 2,598,960 possible poker hands, we're left with the exact same number as we had before, 886,656. So we've answered your questions about horse racing, lottery, poker, but we've only scratched the surface. You know, the possibilities for counting questions in these games are endless as the variations of the games themselves. You might say, well, what happens if you allow wild cards into your game? What if you're playing a game like 7-card stud or Texas Hold'em? Or people seem to constantly ask me questions about how can you apply all this to blackjack? Well, the answer is you can apply some mathematics to solving these problems, but we don't want to take all the fun out of the games now, do we?